Confidentiality, you can't read the other guy's data. Integrity, you can't write the other guy's data. Availability, you can't deny service to the other guy, and so on. As well as resource usage properties, real-time guarantees for your real-time processes, deadlock freedom, starvation freedom. It's a very impressive result. Now, the methodology used, certified abstraction layers, basically allows you to show that a C program correctly implements a functional program. So it's a refinement method based directly on the operational semantics, not with a kind of axiomatic semantics such as Hoare logic or separation logic. And the point is that this is many layered, right? That in a software system that you program with data abstraction, one function in C is a client of some other functions which maintain a private data structure whose representation is not visible to the other function. And that means that the calling function doesn't really even have to know whether that function is written in C or in Galena, in Coq. And that you can, one layer at a time, refine Galena functions to C, and that proof is independent of the proofs of each of the other layers. So this allows the team that builds and verifies Certicos to be very productive, to divide up the work, and they've made a lot of progress. This just shows one layer of the operating system that divides into 11 certified abstraction layers. The total number of independent layers that are verified is nowadays something like 50. Okay, and Certicos is now a fully concurrent kernel with fine-grained locking. It runs in multicore. It supports guest operating systems such as Linux that themselves run in multicore with clients that run in multicore. It all actually even works aside from being verified. Okay, so let me talk about the programming language as a specification interface. This DeepSpec project, the science of deep specifications, pays just as much attention to specifications as verifications, and we look for places where specifications are useful. And I claim that a programming language itself is a good abstraction boundary between the client program and the compiler that implements it. You as the programmer in C, in ML, in Java, in Haskell, whatever, you can treat that programming language as a specification interface itself. Now, one thing that's happened that's interesting in the last decade or so in the C community is the rise of the C language lawyers. So here are some definitions from the internet. A rules lawyer is a participant in a rules-based environment who attempts to use the letter of the law without reference to the spirit, usually in order to gain an advantage within that environment. The term language lawyer is used to describe those who are excessively familiar with the details of programming language syntax and semantics. I'm a language lawyer. This is not a compliment, as you can see. Here are two pieces of code from the Linux kernel as of 10 years ago. In the first piece of code, we have an unsigned int len, we have a char star buff, and this line of code, if buff plus len is less than buff, return. Well, how could buff plus len be less than buff? Right? Len is a non-negative number. Well, buff plus len is less than buff if it has overflowed what you can fit in one pointer value, and it's wrapped around memory. And if that's the case, we don't want to write past the end of memory. So this very reasonable looking code is in the Linux kernel. In the C11 standard, it is an undefined behavior to test, to make this test, this comparison, this pointer comparison. It's illegal. If your program exhibits undefined behavior, the compiler is allowed to do anything it wants because it's undefined behavior. So a few years ago, GCC started reasoning as follows. The program is not supposed to do anything illegal. Therefore, buff plus len can't possibly be less than buff. And since that can't happen, I can delete this line. So the compiler started deleting this line. And the Linux people said to the GCC people, you can't do that. And the GCC people said, yes, we can. The C11 standard says so. Here's another line that was in the Linux kernel. Dereference this pointer, ton. And if ton was null pointer, return poll error before doing any other bad things. Okay, now if you run this in user mode, you'd get a segmentation violation because you're dereferencing an unmapped page 0. But in kernel mode, you don't get a segmentation violation. The dereference works okay. If this was a null pointer, then this sk variable is pretty garbagey. But that's okay, you won't do anything with it because it'll return. But in the C11 standard, it is undefined behavior to dereference the null pointer. And since the source program is assumed not to have undefined behavior, GCC reasons as follows. It's inconceivable that this would be true, that ton is null pointer, and therefore I can delete this line. And the Linux people said to the GCC people, you can't do that. And the GCC people said, yes, we can. So these examples illustrate that it's important to have a really formal specification of your programming language and that's usable by the source programmers as well as by the compiler implementers. And we in DeepSpec claim that you should write down that specification as a fully formal definition of an operational semantics in Coq and prove your source program's correct with respect to it and your compilers. Okay, so we are happy clients of the CompCert verified optimizing C compiler that was developed by Xavier Leroy and his students and colleagues at INRIA between about 2005 and 2030. It continues to improve, it continues to get new optimizations to be ported to new machines and so on. It's software, and as such, of course, it is never done. And it serves as a very important specification interface in various parts of DeepSpec. But it's not the end of the story, right? The LLVM intermediate language is sort of very elegant, very widely used, in some ways more general than the ones used in CompCert. And that's why the Vellum project within DeepSpec is important in doing the same thing, not just for C, but for many of the source languages that compile through LLVM to various target machines. So the Vellum framework is an attempt to get this advantage that CompCert has for a particular set of intermediate languages targeted to one purpose much more generally. Excuse me. Finally, the instruction set architecture of your computer is a very important specification interface. When you program in assembly language, I'll bet you're not thinking too much about how the transistors implement those instructions, which is a good thing. There's an abstraction boundary, the ISA. And therefore, the part of DeepSpec that uses the ISA as a client, such as compiler correctness proofs, and the other part of DeepSpec that implements that ISA from below, find specifications of instruction sets as very important interfaces between modules. So I've talked a bit about the Kami compiler. In this summer school, you'll have I think 3 lectures about Kami, and you'll have the opportunity, I believe, to do exercises in Coq verifying little circuits and learning the principles of specifying circuits as collections of pure functional programs and verifying their properties. In DeepSpec, we also develop teaching materials. We have course modules that use verified interfaces in undergraduate courses that are not really courses on verification. That is to say, in your compilers course, when students are building compilers, you might like them to be using intermediate languages that actually have formal specifications. Not only because that improves the languages they're using and allows them to think more clearly about what they're doing, but they'll have the opportunity in enrichment materials to do proofs in Coq about some of the languages they were using as specifications. And the same is true for the operating system project. So those are examples of applications of DeepSpec even to courses that aren't explicitly about verification. And of course, we have the Software Foundations series of textbooks. This is widely used to teach Coq logic, applications of Coq to programming languages. Almost all of you have seen Volume 1, at least, of Software Foundations. Volume 2 is applications to Hoare logics, type systems, operational semantics in general, soundness proofs of type systems by progress and preservation, lambda calculus, and so on. We're not doing much of that in this summer school. Verified functional algorithms is the application of Coq to proving the correctness of functional programs. And the lectures on verified functional algorithms will start tomorrow. And you'll have the opportunity to prove the correctness of insertion sort, prove the correctness of binary search trees. Volume 4 will be about QuickChik, property-based testing. You'll have an opportunity to use that volume next week in this summer school. Volume 5 is Verifiable C. You'll see a bit of that. The science of deep specification. We want to do the science of how to write rich, formal, two-sided live specifications, how to specify and verify functional programs, C programs, machine language programs, processor implementations, memory models, servers, crypto primitives, crypto protocols, operating systems, compilers, databases, and so on. And in the engineering side, we want to build practical, usable, open source tools and artifacts that embody this science. And we're going to produce the textbooks that teach the world how to use it. So that's DeepSpec. Are there questions? Yes?
So it's an impressive ecosystem stuff. And you talk about linking this up off the specification boundary. Is there any thought being given to interoperability with other verification projects, like SEL4, Project Everest?
Right. So the question is, will some of these DeepSpec projects link up to non-DeepSpec projects done elsewhere, such as SEL4 or Everest? And the answer is maybe. One thing that's proved very difficult, not just for us, but for anybody, is to link up verifications that are done in different logics and different proof assistants. You might think, I used to think, that, well, as long as the specification interface can be written in some simple higher order logic that's a subset of the logics connecting them, it should be easy enough. But no, each specification itself relies on libraries and theories. So that's proved very difficult in the world. And so since those other systems that you mentioned are built in other proof assistants and in other logics, it's more than we're going to attempt to do in the DeepSpec project. Other questions? Yes?
If you will be able to address side channel attacks such as Spectre or Meltdown,
will we be able to address side channel attacks? I think the answer is yes, in the following sense, that in the Certicos project at Yale, they're paying attention not only to functional correctness in terms of input-output, but resource bounds, right? So far, mostly this is upper bounds. Now, for side channels, you need to prove upper and lower bounds. But it still illustrates the kinds of properties they are able to prove and interested to prove in that project. And I can't say exactly what the Kami project is planning to do about side channels, but when Adam Chapala is here next week giving lectures about that, you should ask him. Other questions? Yes?
Do you have any insight in advantages or disadvantages in using a verified C like we see here, and, for example, built-in verifier like they have in Daphne or something like that?
So the question is, what are the advantages and disadvantages of verifying C, as I've described here, or doing something more like the Daphne system? But I'm not sure. The Daphne system is very nice. Daphne contains a little object-oriented imperative language with a kind of Hoare logic-based verification tool that works not so much by a proof assistant, but by connection to an SMT tool. And I've used Daphne for doing some little verifications as a Daphne newbie, and it's great fun. And there even are some tools out there in the world for C that work in that mode, such as the Verifast system of Bart Jacobs. So what are the advantages and disadvantages? I think the advantage of doing this in Coq or in any proof assistant that has a general purpose higher order logic is that you can connect the C verification of, for example, the C program to the functional program to the verification of the mathematical properties of the functional program in your application domain, where you may need the general power of the logic to reason in your application domain. And the other advantage of using a general purpose higher order logic in which everything is embedded is for data abstraction. That when I do modular programming, I abstract away from the representation used in the other module. And for more than 20 years in type theory, we've known that the way to express that is by existential quantification over representation predicates. And so having a logic in which you can do that, I think will scale better to bigger software systems. On the other hand, the advantages of the Daphne or Verifast style are that the proof automation seems to be a bit higher. There seems to be a little less human effort in proving that a program satisfies a specification. Yes? Go ahead.
And what would happen if you take a system like Daphne and you prove in Coq that whenever you prove something in Daphne, then it is actually proven in a logic in Coq?
I don't think I would want to attempt to prove that the whole Daphne implementation is correct. But one could imagine having a tool like that generate a proof witness that can be validated in Coq. There already have been demonstrations of that just for satisfiability modulo theorems. It might be possible to lift up to the kind of boogie infrastructure used in Daphne. But I'm not sure whether people are attempting that. Next question.
Are instruction set architectures properly documented?
Are instruction set architectures properly documented? Well, of course, no. But there's a good project at the University of Cambridge in Peter Sewell's group where for the last several years and continuing, they try to write formal specifications of real processor architectures which are derived from not only running experiments on the actual